kelp. This macroalgae provides the basis for many of the most complex food webs in the underwater world. As a primary producer, the kelp forests that cover some parts of the ocean floor harness the energy that they get from the sunlight, filtering down through the water. These support so many marine species that they are widely recognized as one of the most productive and dynamic ecosystems on Earth. Among these, urchins. These spiny, globular herbivores spend their days grazing amongst the nearshore benthic community of the kelp beds. As they graze on the small shoots of fresh kelp and the drift algae present in the water column, the urchins leave behind a distinct mosaic pattern of patches in the kelp beds. These patches can be used by ecologists to track the patchy distribution of herbivorous sea urchin species. That is, however, until certain predators come to town. Otters. These dynamic predators decimate nearshore kelp forest communities by removing all of the sea urchin populations. Fortunately, otter presence in these communities is few and far between, allowing for a different and much more subtle predator to dominate the upper end of the food chain.
Kelp repeat, the starfish have been spotted at the perimeter. Request immediate assistance. The perimeter has been breached. Initiate escape response. Retreat! Kelp, this is sea urchin. We are under attack. I repeat, we are under attack. Run! Retreat! Tell me a little bit about your experiment.
Well, we've been looking at how starfish predation on sea urchins causes mosaic patterns in a kelp-dominated community.
Fascinating. So how does this happen?
Well, the sea urchins eat drift algae and small kelp shoots, preventing the growth of new kelp plants in small localised areas.
And the starfish predators cause the urchins to move in order to escape, leading to the mosaic patterns.
Great. So we now have a couple of questions from the audience.
So how did you discover that the starfish caused the urchins to escape?
Well, we did two experiments to assess the relationship between the starfish and the urchins. In the first experiment, we added starfish to a subtidal reef which had high densities of urchins to assess the urchin response to the starfish. And in the second experiment, we increased urchin densities in a similar area with few starfish to see if the increase had any effect on the starfish density.
The experiments showed that urchin densities decreased very substantially following the presence of starfish, with some species disappearing entirely. It was also found that the increase in urchin density attracted large numbers of starfish to the area, which subsequently caused urchin numbers to decrease, like in experiment 1.
How do you know that the disappearance of the urchin wasn't simply due to them being eaten by the starfish?
If this had been the case, examinations of the site following the urchin disappearance would have found very large numbers of empty urchin shells or tests, but only a very small number were found compared to vast numbers that disappeared.
Therefore, we can be fairly certain that the urchin disappearance is a result of the escape response, not starfish predation.
Leave! I've been thinking it through and
I finally understand now. It's long been recognised that the uneven distribution of species and communities impart heterogeneity, and the small-scale disturbance of starfish predation on sea urchins is one source of this. Can't you see? In spite of the predation, the starfish and sea urchins live in a dynamic equilibrium overall. It's only in the localised predator-prey interactions that the urchin movement is responsible for the mosaic kelp distribution.
Right, my dear. I just don't give a damn.
So kids, we hope you've learned a lot about starfish and sea urchins today. We'll be back tomorrow tea time and we'll be learning all about how ridiculously unfair it is that we have to sit 2 exams in 3 measly days. Until then, it's goodbye from Vincy and Lillian.
Bye!
Bye from Kevin. And goodbye from us. Bye! Well, that was bloody awful.
Pish.